KHSO4, that's correct. KHSO4, good. That comes from potassium ions are plus, and then we have HSO4 minus. So that'll give us KHSO4. Hey, you know what this looks like to me? This looks like an AB plus CD. Now, A would be the sodium, the B would be monohydrogen phosphate, C would be potassium, D would be hydrogen sulfate. And so, you know, an AB plus CD, that's what type of reaction? Metathesis. So automatically I think metathesis here. And I form sodium, hydrogen sulfate formula, NaHSO4, NaHSO4, sodium hydrogen sulfate, and potassium monohydrogen phosphate. So potassium monohydrogen phosphate would be K2HPO4. I don't worry about balancing. I know I only have one potassium here, two potassiums there, but we'll deal with balancing later. Two sodiums here, one sodium there. We'll balance this if there's a driving force present. If there's no driving force, then I'm not even going to bother balancing it. Do sodium and potassium salts precipitate? No, because they're group 1. Group 1 salts do not precipitate. Do they turn into gas? No, they're salts. Those are stable salts that don't turn into gas. Are we going from stronger acid to weaker acid? No, well, these are amphoteric, hydrogen phosphate, hydrogen sulfate, but nothing changes. When we start off with monohydrogen phosphate, we end up with monohydrogen phosphate. Which one's stronger, which one's weaker? Nothing, they're the same, right? Same thing with hydrogen sulfate. And so what we say here is there's no driving force. Therefore, there's no reaction. But we have to be careful. We have to say that there's no reaction for metathesis. But that leaves three up. Well, there's three possibilities: metathesis, acid base, and redox. So the next one that's probably the easiest to consider is let's consider acid base. We consider acid base. The first step is to inventory it. And so if we think about water, this is a salt. Salts form lattice structures. And so when we dissolve a salt in water, the water is going to pull apart the lattice. Right? And so we're going to be left with, well, let's look at the inventory here. We're going to be left with sodium ions, which are going to be pulled off the lattice. And then what else is going to be pulled off the lattice? Monohydrogen phosphate ions are going to be pulled off the lattice. Now, will the hydrogens, is water strong enough to pull off the hydrogens off monohydrogen phosphate? No, that's because monohydrogen phosphate is a weak acid. Water is only strong enough to pull the hydrogens off strong acid. This is not a strong acid. This is not one of the 70 memorized. And so we leave this hydrogen on here. Maybe it'll pluck a couple off. You know, let's say I had 1,000, maybe it'll pluck a couple off. But we're just looking at the major species, not the minor species. And so leave that alone. What about potassium hydrogen sulfate? Does that get broken apart or does that stay together? It stays together? Well, when we think about potassium hydrogen sulfate, I think also salt. And if it's a salt, it's going to form a lattice. If it forms a lattice, in order to get that lattice to dissolve, can we have crystals floating around in the water and call that dissolved? No, that would be heterogeneous. The crystal's got to be broken apart. And so the water is going to pluck off the potassium ions, and then it's going to pluck off the hydrogen sulfate ions. Will the water pluck off the hydrogen sulfate? Will the water pluck off the hydrogen? These are the apples. Will the water pluck off the apples here, the hydrogens? No, that's because hydrogen sulfate is a weak acid. It's borderline strong, but we still consider it weak, so we'll just treat it like that. And so we have these ions present and one more, water. And so let's take a look at the chart. You know what you should do with these charts is you should read them once in a while. Read the entries. And so, you know, every once in a while I'll read the entries just so I familiarize myself with the chart, like this. This is perchloric, hydroidic, hydrobromic, hydrochloric, sulfuric, chloric, nitric, hydronium. This one you probably don't know. This one's called trifluoroacetic acid. Hydrogen sulfate or bisulfate, phosphoric acid. This one you learn in Chem 1B. This is called hexaaqua iron 3 ion. Hexaaqua iron 3 is acidic. This is, you know, what happens is sometimes people don't read the chart until the day of the exam. This chart's going to be given on the test. And then they get confused when they see it. Throws them way off. What's this? Nitrous. Hydrofluoric. This is a one carbon acid. In organic chemistry, one carbon is given the meth. This is called methanoic acid. Methanoic acid also has another name. Methanoic acid is also called formic acid. Formic acid. This is a 2-carbon acid. 2-carbon acids are in organic chem called, not meth, but F. This is called ethanoic acid. Ethanoic acid has the common name acetic acid. This is acetic acid, C2H3O2. C2H3O2. This is carbon dioxide. Carbon dioxide is what we call a Lewis acid. Carbonic acid is what we call a Bronsted acid. Hydrosulfuric, dihydrogen phosphate, ammonium. Hydrocyanic acid. This is cyanide, one's hydrocyanic acid. Or hydrogen cyanide, aka hydrogen. This is also called hydrogen sulfide, hydrogen cyanide. This is, we don't need the mono here because dihydrogen would be this, carbonic acid. So this is called hydrogen carbonate or bicarbonate. Etc. So once in a while you should read all the entries. And keep off. Anyway, if you read all the entries, then we know, does sodium ion occur on that chart? Monohydrogen? Yes. Occurs here and here. So if we read both sides, we would have seen, oh, monohydrogen occurs on both sides. To save us time. Some people never read, and then they're in a rush, and so they only see it once here. They don't realize it's over there too. So this is what we call amphoteric, both an acid and base. Potassium ions, not applicable. HSO4 minus, acid base. Water, acid base. So we have 3 acids, 3 bases. Which one's the strongest acid? Let's take a look. Yeah, if you know the chart, HSO4 minus is the strongest acid on this list. A stronger acid. This list, HSO4 minus is the acid. What's the base? Water. Water is a pretty weak base. It's way up here. Hydrogen sulfate is an even worse base. HPO4 2 minus. Looks like it's got to be the best base here. HPO4 2 minus. And so let's take the acid HSO4 minus and the base HPO4 2 minus and then react it. What should form here? It's going to form here. Yep. And so we're going to form sulfate. So the acid loses the hydrogen. Charge goes more negative here. And then the HPO4 2 minus gains it. So we'll form H2PO4 and the charge goes down. Okay, sulfate, can it occur as on both sides? No, because sulfate doesn't have any H. So this is only base. This is amphoteric. But in this case, this will be the acid. And so if we reverse this, this is the acid-base combination. And then let's compare the two acids. HSO4 minus. H2SO4 minus, is that right? No, HSO4 minus versus H2PO4 minus. Well, HSO4 minus is up here, H2PO4 minus is down here, which means that this is a stronger acid. This is a stronger acid. This is a weaker acid. If the acids follow this, the bases must follow. So this has got to be stronger, this is weaker. If I made a mistake, then it wouldn't follow. This is why when I told you the driving force, we only look at the acid, because it's easier. Look at the acid versus looking at that. The bases have to follow. So we get driving force here. And so there was no reaction for metathesis, but there was reaction for acid base, peroxide acid base. All we need to do is find one. I'm not even going to bother looking for redox here because we got a reaction here. Although, to be thorough, we would look for redox because there could be competing redox reactions that have driving force. And so you have multiple reactions occur, and that does happen in nature. Okay, how about this one? Why don't you do this one? Solid sodium amide is mixed with water.